All right, last chapter, chapter 17. Principle of linear superposition and interference. Unfortunately, not the kind of interference you see in the picture there, but hopefully you get the idea. Principle of linear superposition, basically when two or more waves are simultaneously at the same place, trough, trough, peak to peak, the resultant disturbance is the sum of those disturbances from the individual waves. You have two types. You have constructive and you have destructive interference. This right here is going to be your constructive interference. And notice that you're adding a wave here to here. So here's your peak to peak. And it grows about twice the size. And you're adding a wave with trough to trough. And the trough grows about twice the size. So this is constructive interference because you're amplifying the sound waves. I have made a video. It's really difficult to make with the tones. But that'll actually show you this. That I'll show in a second. Hopefully it's going to play. I've never tried to play the video through a video, but we'll find out. The other part is destructive interference. So we've got a peak lining up with a trough or a trough lining up with a peak, and you just get flatline. This is directly canceling out everything because it's half of a wavelength away from each other, and since it's half of the wavelength, it completely cancels out. This is like jamming, like radar jamming or something like that. You're canceling out that wave. Using Audacity, I was able to kind of create a video a while ago that shows both of these. So hopefully it'll play okay, but let's think it's loud enough. Let's hope. Well, we're going to find out if it's loud enough. Here we go. This is a 250 hertz tone. Note the amplitude of the sound wave and also note the volume of this sound wave. Now, two 250 hertz tones are being played side by side. Clearly, it is louder. Now the waves have been physically combined. Note that the volume is identical, but the amplitude is off the charts. When waves combine like this to amplify, it is called constructive interference. What happens when the trough of one wave lines up with the ridge of another wave? The answer is that you will hear nothing. Since the trough of one wave is lining up with the ridge of the other wave, the two sound waves cancel each other out. Now I will cut a little bit of one wave and then play them simultaneously to see if I'll hear a sound. Now that they don't cancel out, we do hear a sound, yet it's not as loud as when we had the two identical waves combined. This is called destructive interference. I clicked undo, and we are back to where the waves cancel. This is called perfect destructive interference. Okay, so hopefully you heard that. We're going to find out here in a second when I double check on it myself. But basically, this is kind of showing you what it's like when two people sing and together and are singing the same tone. You have your constructive interference, but if they're out of tune by half a wavelength, it creates a bunch of stuff no one wants to listen to. But yeah, so normally I would play that in class, but it's hard to do online because, well, now I have to play a video in a video, interestingly enough. So yeah, and the reason I'm so subdued there is because the tone was throwing my audio off like crazy. I had to be so subdued and I couldn't have any emphasis in my voice, otherwise it would throw the audio out of whack. I don't know, that was hard to make, to be honest with you. Alright, doing a problem. Two in-phase loudspeakers, A and B, are separated by 2.4 meters as shown in this picture. Voila. A listener is at point C, which is 3.2 meters in front of B. The triangle ABC is a right triangle. Both speakers emit 214 hertz tones. Does the listener hear loud or no sound at all? All right, so what I need to do, for the sake of humanity, because apparently that's what we're doing now. We're saving humanity by doing physics. Awesome. I love being a hero. So I need to figure out that distance, AC, we'll call it. Well, we're just going to call it C because C was what's used in Pythagorean theorem, and that's exactly what I'm going to do. That'll be 2.4 meters squared plus my 3.2 meters squared. And I chose an easy number because I wanted it to come out to be a clean 4 meters. All right, so we now know the distance 4 meters. What I need to do is figure out at what point will the wave be when it hits this person. Will it be, let's say, at the trough or the peak? And so I need to first figure out the wavelength. We know that V equals F lambda. So V over F must equal to lambda. And so if I take my 343 meters a second and I divide that by my frequency of 214 hertz, I get, once again, an easy number I chose, just it was the only way it was going to work, 1.6 meters. So that's the wavelength. What that means is if I'm going to draw a really cool thing using my little line trick that I have here that you guys are probably not impressed with at all and should very much be so. Well, this is at 0. It's going to go up, down, and cross, and it's going to be at the exact same phase as the original tone was emitted, and that's going to be at 1.6 meters. Then it's going to go, let's see if I can keep it constant, up, down, back up, and that's going to be at 3.2 meters. And then up, and I'm going to extend this out a bit. This will be at 4 meters. Okay. So, a couple of notes here. We know that at 1.6 meters, it's going to be exactly in phase when it hits, if someone were standing 1.6 meters away or 3.2 meters away. This man, or figure, is standing 3.2 meters away. So from B, it's going to be 100% in phase with the original tone. And think back to the little graphic that I showed you with the audio audacity and the wavelength and how the waves would line up. Basically, it's going to be in phase with its original tone. So it's going to be, we'll say it in phase. That's the real technical term. I was going to try to come up with something better. Not technical, but I don't know how to word that. Too much Star Trek. Too much Star Trek. Well, the other one's a little bit different. So we said 3.2. Well, 3.2 is actually going to occur right here. But it's 0.8 meters away. And now notice that if I take 1.6 meters and divide it by 2, I get 0.8 meters. Which means that, well, this is, say, at 1.6 meters. Its complete opposite is going to be at 0.8 meters. Yes, it's going through the equilibrium line, you say. Well, in this case, it's going down through the equilibrium line. In this case, it's going up through the equilibrium line. It's completely a wavelength that is half of the wavelength of the 3.2. So this one is going to be completely out of phase. So what's happening here is you have a wave where essentially you can think of it as a trough is a peak is hitting the trough. And so what's happening is this listener is not going to hear any sound. That's just because it's going to be experiencing two different sounds from completely two different phases that are completely out of phase with each other, thereby canceling it. You're thinking, well, why the hell have I never heard this before when I've had two speakers? Couple reasons. Number one, we have walls and sound bounces off walls. So if you have a soundproof room, you might be able to pull this off. I really wish I did do this. I wish I had a soundproof room. I would totally try this out. But that's the only way I can think of that's going to work. That's one. Two, you don't listen to Hertz tones. You just heard them, and you probably slammed your ears and like, oh my God, why the hell is he showing me this? This is ridiculous. Well, that's because those tones are very abrasive when you hear them. And that's another thing. You don't listen to tones like that. It's the music you listen to has waves all over the place. If you listen to tones, you may have actually experienced it. Maybe something sort of like that. So, anywho, that's kind of the reason you haven't experienced that. And I really wish I could try to do this in real life, but I don't have a soundproof room. I have walls. I hear echoes. I mean, like my first 3 chapters, I had an echo when I lectured because it took me a while. But anywho, fun time. Okay, diffraction. And I've kind of talked about this already. Basically, when a wave bends around an object, that's called diffraction. At the beginning of chapter 16, I talked about the cylindrical water cloak. Basically, it uses diffraction to bend the water waves around the object. There are 2 equations for diffraction. One is going to be sine theta lambda over d, and I'll tell you what those are here in a second. And The other equation is the same thing with a 1.22 factor in front. The lambda, of course, is going to be your wavelength of said wave. And d is your width, which is kind of weird. For a circular opening, the d stands for the diameter, still the width, and that's where the d comes from. So for a regular non-circular opening, so let's say just a narrow slit, it's going to be sine theta is equal to lambda over d. And for a circular opening, there's that 1.22 factor. It does say at the first minimum. So when these waves come through, it's going to have constructive and destructive areas. The first minimum is going to occur in the first dark area. Those are the minimums. Those are the waves are, where the troughs of the waves are. You can think of it that way. Whereas the brighter areas are the maximum. So the minimum of the maximum is basically the trough and the crest between the two. This sets up a kind of two situations here. And let me write these out. So let's say if lambda divided by d, and let's make that small. Basically, you would have some sort of narrow opening. And if lambda over d is really small, that means lambda, your wavelength, is probably going to be really small. So basically what you get are small waves that just pretty much pass straight through your slit. Because of that, you're not going to have a lot of dispersion. You're going to have narrow dispersion. And the reasoning is that, and you'll learn about this in physics too, is that the waves of, say, like electromagnetic waves, like light waves, are also particles. It's called particle wave duality. And because of it, you could think of the individual particles just aren't big enough to be rejected or diffracted through that little slit. Now, the opposite's going to occur if lambda over d is large. So we'd have a narrow slit here, and you'd have large wavelengths. Well, when you have a large wavelength, you're going to get a wide dispersion. And it also, and you're thinking, well, it also has a factor with the d, the width, or the diameter. Yeah, it does. But mostly here, I'm just doing it for the focus of actually individual wavelengths. Assuming that you have roughly the same diameter in those situations. So those are kind of the two situations with diffraction. But a diffraction pattern, like I've showed you earlier on the PhD simulation, looks similar to this. The waves come through and they just kind of spread out around said barrier. So let's do a problem. Let's say you have a door frame and it's 3.5 meters wide. Soundgarden is played in the room behind the door frame. Lead vocalist Chris Cornell. I did change it to 3.5. Okay, I originally had a different number. Lead vocalist Chris Cornell was known for being able to sing in 4 octaves. So assume his frequency ranged from 110 to 880, which is 4 octaves. He wasn't the only one. For the life of me, I can't think of his name, but the Queen, Freddie Mercury, I believe. Yeah, I think he could do it too. But Chris Cornell, I know a little bit more because I tend to listen to metal. And this is grunge, but it's close to metal, some songs. Well, anyways, we're going to find the diffraction angles for the two frequencies. So this is a narrow slit and not a circular opening. So what we're going to use is we're going to use sine theta is equal to lambda over d. But a kind of issue is, well, we don't know the wavelength. But we know it's sound, right? And I also know that v equals f lambda, or v over f, is equal to lambda. And we do have frequency. So what I want to do is take sine of theta, and then for lambda, I'm going to put in v over fd, food. And I totally botched that. Equals theta. There we go. Now that's what I'm going to use for the two different frequencies. So let's go ahead and calculate that. Let's do theta 110 And for theta 110, we're going to take the inverse sine of 343 speed of sound divided by the frequency, so that's going to be 110 hertz. It doesn't look like quite 110, does it? And then times the width, and we say it's just a door frame, so 3.5 meters. Okay, have a calculator on here somewhere, but remember you need to be in degrees again. 343 divided by 110 divided by 3.5, and then I'm going to take the inverse sine of that shenanigans, and I get around 63 degrees. Let's do theta 880. So it's the same things, inverse sine of 343, that hasn't changed. The only thing that's going to change is your frequency. So that's 880 hertz times 3.5. All right, same deal. 343 divided by 880, divide that by 3.5. Gave me an error. Why? Because it doesn't like me. Now it likes me. Inverse sine of that and gives me 6.4. It's really close to 6.3 as well, but we'll say 6.4. Okay, so basically put, this is very, very, this is a large dispersion, 63 degrees, means that when it goes through a slit, it can have a variation of, say, 63 degrees as measured at this angle. Whereas this one's very small. It's going to go through the slit and like be maybe like this, that range or something like that. So this one's going to have a very small or narrow, I think the better term to use is narrow dispersion. Now, to deal with a narrow dispersion for high frequencies, they will often use tweeters. And you'll see tweeters, those little top little piece of little speakers. The tweeters are actually used to for those high frequencies, since the dispersion is so narrow. And basically, they have a diameter that is smaller than, say, the regular speaker. So, anywho, I really like doing problems. I like Soundgarden. But yeah, you should too. All right. Beats. And I'll show you an example of this in just a second. In fact, I'm going to do two back-to-back examples. Two overlapping waves with slightly different frequencies will give rise to what's called beats. And I call it the periodic variations in the loudness. And I haven't really defined loudness yet. I'm going to. And the number of times per second that the loudness rises or falls is the beat frequency, and that is the difference between the two frequencies. So, like I said, I made up my video a long time ago. I want loudness. Where are you? Here you go. Note the amplitude and the volume of this 250 hertz tone. The sound wave has been amplified by 50%. Note that the volume and the amplitude of the wave have increased. The sound has returned to its original form. Note that the amplitude has decreased. Therefore, the volume of your voice corresponds to the amplitude of the sound wave. Okay. And so that's loudness. So the larger your amplitude, the louder you are. For frequency, I made another video as well. This is a 10 kilohertz tone. Notice its wavelength, which is indirectly proportional to its frequency. Now the pitch is dropped 50%. Notice that the wavelength is now increased and the frequency has decreased. The pitch has dropped 50% and the frequency has decreased again. Therefore, to change your pitch is to physically change the frequency of the sound wave. All right, so that basically says, so frequency is the pitch. And you notice that. They just continually decreased pitch, and you can actually see a change in, say, the wavelength and the frequency. Loudness, of course, corresponds to how broad your voice is. I have one for beats as well. If I find it, I shall show it to you. This is a 250 hertz tone. Note the frequency and wavelength of the wave. This is a 440 hertz tone. Note that the sound is higher pitched and that the wavelength is shorter. Now, both tones are played simultaneously. The bottom wave is the two waves physically added together. Note that the wave shape is distorted. I have slowed down the wave by 100%. Note the tone, as if it sounds like a humming light. I have slowed down the wave by 100% again. Now, it sounds like a diesel truck. I have slowed down the wave by 100% again. It sounds like a fan, with loud and soft spots. Those loud and soft spots, which were undetectable before, correspond to the highs and lows of the sound wave. These fluctuations are called beats. Okay, so you could kind of, the last one's harder to hear because it was really hard to make. And normally I would, well, I have another one that I could play without my voice. I don't really know how to, I can't find it for some reason, but I could talk through it. But in either case, so your loud, or not your loudest, I'm sorry. So your beats, that's the that's what you're hearing. And that's the number of times per second that the loudness rises or falls, and we call that the beat frequency. The difference between the two frequencies is going to be the beats. And that's what you're hearing is the and the beats is nothing more than literally adding the two waves together, and the fact that it's not the same, like, you know, when we had like the regular, 10 kilohertz tone, it was like, well, this one's not. It's like, because they're adding together really weird. And it's not clean. It's a partial destructive interference, to be honest with ya. Anywho, yeah, moving on. Okay. Two tones are sounded together as shown below. We're going to figure out the beat frequency. So this is a graph of the pressure versus the time. This is the pressure wave. And what we need to do is figure out the frequency of each of these in order to figure out the beat frequency. I can notice from here that it's telling me that it's going to take 2.3 seconds from the crest to equilibrium, and that's 1/4 of the total wave, because this would be 1, 2, 3, then 4. And so different ways you can do this, but this is how I do it. Okay, well, let's figure out the period, because I think it's easier to figure out the period from the graph of the wave than anything else. So I know it's going to have to be 4 times 2.3 seconds to get the total period, and I can do that one in my head, and it's 9.2 seconds. So the frequency is 1 over the period, and this one I can't do in my head, but if you take 1 divided by 9.2 seconds, you will get 0.11 roughly hertz. Now we're going to do the period of the second one. This one, if you notice, goes peak to peak, to peak. So it's going to go from here, or rather trough to trough. I said peak to peak. You get what I'm saying. So it's going to measure from this point all the way to this point. So it's really just from peak to trough that you'll notice, because we're only going to go through half the cycle. We haven't come back down to the original position. And so this one is then going to be half of the overall wavelength. So I'm going to take 2 times 1.7 seconds, and I can do that one in my head to give me 3.4 seconds. What I can't do in my head is 1 divided by 3.4 seconds. I can approximate it, but not very well. And that gives me 0.29 hertz. Now, to figure out the beat frequency, you just take the difference between the two. So your beat is going to be 0.29 minus your 0.11 hertz. And so that's going to be what? 0.18? Sounds good to me. So your beat is the difference, and that's going to be your 0.18 hertz. So when I ask you to find the beat frequency, you just find the difference between the two frequencies. And once again, we're assuming these two frequencies are added together. Okay, transverse standing waves. Oh, this makes so much more sense than what I thought it was going to be. Okay, good. I thought my slides were out of order and this was second. And I was like, why would that be second? It doesn't make a lot of sense. I was going to cover this anyways. Okay, transverse standing waves. A transverse standing wave occurs in instruments such as guitar. That is the key go-to for me, is to think of a guitar string or a rubber band that's stretched out and you're kind of plucking it. You have nodes, and there are places where there is no vibration. And so the node is going to occur, and I kind of labeled it here, right here, a place where there's no vibration. Those are your nodes. The antinodes are at the maximum vibration. So your antinodes are where you're going to have the highest vibrations, and your nodes are where you're not going to have very little vibration. Hard to kind of visualize a little bit. So at this PHET simulation, I had to start it ahead of time. This is what's known as the first harmonic, which I'll talk about earlier. But this is what it's like taking a standing wave. You can imagine me like plucking this up, and then if it has no damping, it's just going to go up and down forever. Why is it all wobbly? Because this simulation was not made to create a standing wave, and it took me like 10 tries to get something that I kind of wanted like a jump rope is really what I wanted to go with this. I can maybe try to make it wavy, but it's not easy. And now it's all, yeah, see, it's a wave, but it's all adding together funny, and it's pretty hard. But that's about the best example I can come up with. You can think of this as a guitar string and you're plucking it. Nodes, antinodes. Oh, harmonics. I said I was going to talk about that. This is your first harmonic, frequency F1. We call this the first harmonic. Your F2 happens to be 2 times F1, and that's known as your second harmonic. I'm just going to put second harm. And your third frequency is going to be the third harmonic, which we call 3 times F1, and that's going to be your third harm. So depending on essentially how many loops you have, is what your harmonic is. So when we pluck that guitar, or when the tool rose up and down to create that simulation, it created essentially one loop. So that creates one harmonic. I tried but failed to get it to be 2, the second harmonic. That's if I could get it to be a nice sine wave or a cosine wave, whichever one you prefer. Third harmonic has 3 loops and so forth. So each additional loop adds on to the next harmonic. That's all you need to know there. Now, why are we learning about harmonics? Because there's equations for this. Transverse standing waves. For a standing wave with a string fix, such as the one I showed you in the PHET simulation, we get Fn is equal to NV2L/3, where N is a positive consecutive whole number, integer. How do we get that? Well, when I showed you the simulation, which is still up, basically put, it's going to travel, and it's hard to see here. I should maybe try to do this. That's okay. Basically, it's going to travel and then come travel back because that's how any wave goes. It's going to go this way and then loop right back. Okay, so it's going to travel twice the length of whatever said string it is. So that's my start. Wish I had a better representation, but this is the best I've got. So, and if I take that twice length of the string and divide it by v, the velocity of said wave, I actually get the period. Therefore, since frequency is equal to 1 over the period, I know that frequency is going to be v over 2L. And when I showed you that example originally, I did it for the first harmonic. And so for the first harmonic, F1, we get 1 v over 2L, or f, the frequency is simply equal to the velocity divided by 2 times the length. So this is your f sub n. Your n is the harmonic. So it'll either tell you, that's a really not well, and well, it's not good. You can't read it. There we go. Your harmonic, remember, is the number of loops that you have, say, in the string. So you don't see a lot of loops because when you're thinking of a guitar string, it's kind of hard. I tried it on this one. I don't think I could be successful because it's just so weird. And if I restart it, I still have to hold the damping down to 0. And that's a little better, but in any case, you'd have to count the number of loops. This is still more or less 1 loop, almost 2 loops. And based off the loops, you'll figure out which harmonic it is, and then you can apply this equation to get the frequency of said wave. And they have to be whole integers because if you're counting number of loops, you're not going to have a half a loop normally in these circumstances. All right, so that kind of gives you an idea. I've talked about the fundamental frequency. Oh, yes, I think I mentioned this, but I didn't want. When n equals 1, we call this the fundamental frequency. So, and that fundamental frequency, since it's v over 2L, and since we know that lambda is equal to v over L, and since it's v over 2L, it's actually going to be occurring at 1/2 lambda for your fundamental frequency. So half the wavelength off. Which makes sense. Going back to here, I'm going to restart it and hope I don't screw this up. But when I tried to do one beautiful wave, it's essentially just 1 loop. And so notice that since it's 1 loop, you're only getting to half of the wavelength. So that's why when you actually mathematically look at it, you get v over L, but it's actually v over 2L, so it's at half the wavelength in order to find that fundamental frequency. So it's occurring at that node. So we should do a problem on that because we like problems. Okay, I like problems. I hope you do. Maybe you don't, but I do. All right, we have 2 wires, each of length 1.25 meters, are stretched between 2 fixed supports, so like a guitar string. On wire A, there's a second harmonic standing wave whose frequency is 440 hertz. However, the same frequency of 440 hertz is the 4th harmonic on wire B. So what I need to do is find the speed of which individual waves travel on each wire. Okay, so our equation, coming down here, where's my... There, where'd you go? There you are. F sub n is equal to n v over 2L. That's what we're going to be using, but we're trying to solve for the velocity. So solving for the velocity is then going to give me 2FL, there we go, over n is going to be equal to your v. Okay, so let's figure out the v of A, for wire A. All right, so I take 2 times my frequency, and that's 440 hertz, times the length of the wire, 1.25 meters, divided by the harmonic, and it says second harmonic, so I'm going to put a 2 here. I'm going to see that 2's cancel because I'm lazy and I don't want to do arithmetic. And now I'm just going to take 1.25 times 440, and I get 550 meters a second. And then the same thing for VB. We have a 2 times 440 times 1.25, and it says it occurs on the fourth harmonic. So the harmonic corresponds to n, so I divide it by 4. And so basically now I'm just going to take 440 times 1.25, and then I'm going to divide it by 2, because it's 2 of 4 is 1/2, and you're going to get 275 meters a second. Therefore, if you hold the frequency constant and increase the number of harmonics, your wave speed will decrease. It's kind of something, the main thing to get out of this problem. There is another one before I move on to the next topic, if it lets me scroll. It's kind of like one in your book, one of the examples. We have a string under an unknown tension, produces this wave below. The string is, let's say, 1.5 meters long. Let's say it has a linear density of 3 times 10 to the negative third kilograms per meter. And let's say the speed is 225 meters a second. We want to figure out the tension the string is under and what is the frequency and the wavelength of the standing wave. Okay, so it's been a while, but we remember from a couple of chapters ago that V, I think it was just last chapter, is equal to T over mu, where mu is the linear density. That's what we're going to use to get that tension. So multiplying out, that gives me V squared mu equals T. So V is 225. Mu is my linear density of 3 times 10 to the negative third kilograms per meter. And I get, let's see here. And I totally forgot to square the V. I know what you were thinking. What? You forgot to square the V? Yeah, I did. It was such a tragedy. Tragedy. Something bad. Okay, so I square the 225, multiply by 3e negative 3, and I get a interesting value of around 152 newtons. So that guitar string, which is what I'm calling it, it may not be a guitar string, is under a tension of 152 newtons. All right, so that gives me the tension. And then part B is asking, what is the frequency and the wavelength of the standing wave? Well, I know that V equals F lambda, because I just know that. And then I know that F must be equal to V over lambda, because F lambda is V, right? And so I take my velocity of 225, and I'm going to divide that by lambda, my wavelength. Now, lambda is going to take me something, some little thought mechanism, thought experiment, thought mechanism, thinking. Let's call it that. I know that it says this entire wave is 1.5, right? So from here to here is 1.5 meters. Now, it starts here, circles up, comes down, comes back around here. So it does a complete wave, a complete cycle in 2/3, right? So all I have to do then is take 2/3 times the whole length of 1.5, and that gives me an actual wavelength of 1 meter. Once again, since I know the whole thing is 1.5 meters, and I want to find the wavelength, I would just say, okay, well, 2/3 of this wave occurs at this point for 1 wavelength, and so if I apply it to the overall length, I'm going to get the wavelength. So if there was another, let's say there was another little loop right here, and let's say it was still 1.5, actually it wouldn't change much, but if it did grow, I would actually I would apply it by like the 2 meters or however big it grows. So you just need to find one complete wavelength, And you can just kind of use logic. Well, if this is 1.5 and I break this up into 3 points, then this is at 0.5, this is at 1, this is at 1.5, this is at 2, and then et cetera, et cetera, et cetera. Well, in the end, your frequency is a 225 hertz. Okay, so that gives me my 225 hertz, and it says wavelength. Oh, I already figured that out. That's 1 meter because I couldn't get my frequency without it. So here we go. That solves that problem. Okay, longitudinal standing waves. We've talked about standing waves that were transverse, such as like a wave on a string. In this case, we're going to deal with longitudinal standing waves, which deal with sound waves. I've drawn some pictures here ahead of time because I tried this without pictures, and then I had to draw it while I was talking to you, and it always goes badly. Usually when I teach class, I will draw the pictures first. Then I'll start talking because then it just goes badly. In any case, I found a picture that I'm going to talk about first, then talk about the pictures. It's actually, most people say GIF or GIF. I always said GIF. I don't know. I guess I'm old. Okay, so basically you can think of a woodwind instrument or just a pipe with air in it. Inside that air column, it's going to vibrate. You could think of these particles as being inside of the air column. And whether or not the air column is closed off at both ends, open at one end, open at both ends, there will be reflection, a lot of reflection, coming back and forth between between the two ends of the pipes. A little bit beyond the scope of the class why it happens with a pipe that's open on both ends, but it does happen. And so if you look at this is just like the vibrating particles in the air column. Notice that this red particle right here is vibrating back and forth, and this red particle is stationary. Now, these are two graphs. This is the pressure graph. Inside of the tube, it will have pressure differentiations due to the sound waves. Whether it rotates, well, it's going to rotate back and forth, and as it does, the pressure will increase and then decrease to its maximum amplitude. As a result of the pressure changes, you will notice that when this is at its lowest point, it's going through equilibrium up here on the actual particle displacement. So the particle displacement is shifted 90 degrees or pi over 2 from the pressure, which makes sense because the pressure is going to impact the particle displacement. And so, couple things with that. This is the actual particle displacement. And notice at this point right here, this is where this node is occurring. Remember, nodes are a point where basically the kind of waves kind of meet. They have minimum amplitude where it kind of crosses equilibrium, whereas your antinodes are places where it's at maximum amplitude. And so this node is not moving, and neither is this wave moving, or a particle even on this wave moving up and down. So it makes sense that this red dot is just kind of stationary. And that only exists for the particle displacement wave because that's what's going to generate our standing waves, which is here. Okay. So these are longitudinal standing waves, and I kind of shown you where it came from. There are two equations, and I'll kind of show you where it is. These on the left are for tubes open at both ends. And these are for open at one end. And I didn't write the word open. So this is for open at both ends. So this is your fundamental frequency, n equals 1. For a open at both ends, one thing you need to know that is that antinodes must occur on the end. That's just an accepted fact. So it has to start and end with an antinode. And so if you start in your fundamental frequency, you'll cross and create a node, and then you'll get to your other end and you'll have your other antinode. Notice that this is only half of a wavelength. So to get from antinode to antinode, it's going to only be 1/2 of a wavelength. If we double that and get to the next antinode, we'll reach the second harmonic, n equals 2, and that gives you the fact to get to that second antinode. And so in this case, we have 3 antinodes and 2 nodes. This would be a full wavelength, but that's to get to the second harmonic. And that doesn't really apply here. This does, the lambda over 2. Because the equation, when we come down here, we know that frequency is equal to the velocity of, say, a sound over the length. And for a tube open at both ends, it's occurring at half wavelengths between the 2 antinodes. And so that's why this has a factor of 2. It comes from the fact that between those 2 first antinodes, it's only going to be half of a wavelength. So it's identical to when we did waves on a string. The same sort of frequency equation for waves on the string. So open at both ends is the same for waves on a string or the regular standing wave. These are open at one end. It gets a little bit more complicated there. When it's open at one end, the closed end must be a node. Once again, just kind of a given. So you start with a node, and when you hit that first antinode, it's only going to be 1/4 of a wavelength. So that's why this one, for the frequency, has a factor of V over 4L. And since it occurs, and since it starts at an antinode, and if we go to the third fundamental frequency, 3F, I'll talk about that in a second, but in order to get to the second antinode, it's always going to be at odds, or a little oddly shaped, because we started at a node, and so it's always going to occur in terms of odd integers. And so notice, going back here and erasing, that, and I haven't talked about this completely, for it open at both ends, it's just like the regular standing wave, 1, 2, 3, all integers. But if it's only open at one end, we can only use odd integers. That's why this will be the third frequency. And then if I added another little node and an antinode, that'll be 5F, and then so forth. And so that's kind of the difference between the 2 types of waves. All right, we'll do a problem. We have a thin 1.2 aluminum rod sustains a longitudinal standing wave with the vibration antinodes at each end of the rod. There are no other antinodes. The density of Young's modulus of alumina, respectively, 2,700 kilograms per cubic meter, and 6.9 times 10 to the 10th newtons per meter squared. What is the frequency of the rod's vibration? So you might be thinking, how the hell do I know if this is open or closed? It didn't say, and that's true. It didn't. But there are keys here. It says antinodes at each end. Rolling back up here, if it's a open at one end, it has to have one end with a node. And so that automatically means that the equation that we're using is going to be Fn equals NV over 2L. So that much I know just because of the way it told me. But then what kind of harmonic are we on? Okay, well there's another way to figure that out. There are no other antinodes. So it says the ends are antinodes and there are no other antinodes. And so I've kind of drawn 2 out here, where n equals 1 equals 2. With n equals 2, there is an antinode in between the 2 ends, which are antinodes. So that can't be that. The only one that's going to occur is at n equals 1. And so we also know now that n equals 1. Finally, it says we need to get the velocity. Well, it didn't say that, but they wouldn't have given us the Young's modulus and the density otherwise. And from earlier, from a last chapter, I believe, we know that the velocity inside of a solid is going to be the Young's modulus divided by its density. And so I can rephrase that to write n root of y over rho over 2L. And it gave me my length of the rod. I have all the information I need, so let's plug it in. Frequency, this will be 1 root, that's going to be 6.9 E10 newtons per square meter divided by the density, which is 2,700 kilograms per cubic meter, all over 2 times 1.2. I think, yes it is. And let's plug it into a calculator to get an answer. All right, 6.9 E10 divided by 2,700 rooted divided by 2 divided by 1.2 gives me 2106 hertz. Pretty high. Okay, so the problem doesn't give you whether it's open or closed. You could just use context clues based off of the nodes pictures, which are also in the book. It's pretty much identical what's in the book, in order to figure out what type of whether it's open at both ends or just open at one end. All right, exam 4. A little bit different. It's almost like a quiz. Last time I taught this, I had a test over 10 through 17, which I thought was just too much. I really should somehow divide 10 through 17 in half, but it's really hard for me because 10 through 15 seems to cover the same amount of material or the same type of material. So I'm kind of struggling with that. It'll be worth less. I still drop your lowest test score despite that. Whichever one helps you the most, because they're not all worth the same. And that kind of went to crap last test because I made a mistake on a problem, had to throw one out. But it'll be a little bit different. It's only going to be 50 minutes. And it's only going to be worth 45 points. And amazingly, I did not put the one thing I started with, but yeah, actually it is there. 6, 5, and then 2. I feel like I'm off by a hair. I believe it's 15 questions because I'm counting 14. Maybe it is 14 questions. Okay. Well, in any case, you have 6 multiple choice that are conceptual. Meaning not a lot of math for it, more just kind of looking at it and kind of knowing it. And then you're going to have 5 computation, which will be multiple choice. Once again, over chapter 16 and 17. And just like last test, you'll have 2 numeric entry problems. Both will come from the lectures, so if you've watched them, it should be very similar to a problem in the lecture. One will be coming from chapter 16, and one will be coming from chapter 17. It will be the same way the tests are. It'll be on December 1st. That part I didn't tell you, but it's on your schedule. It'll be on December 1st. It'll open up at 8 a.m. and close at 8 p.m. Talk about your final later. Your final's going to be different than the rest of the tests. Probably going to have you write that one out because I hate using that test thing generator, and I want to do at least one, and kind of like a homework. So, anywho, that is it.